Hello, my name is Prabjot Kaur. Welcome to another lecture on the series of fundamentals for embedded systems. In the last lecture, we started with the basics of electronics theory. We kind of know the fundamentals such as what is electric current, voltage, power, and then we started with the basic electrical components, specifically the passive electrical components. And we spent majority of our time learning about resistors. Today we are going to cover rest of the two passive electrical components, namely capacitors and inductors. First, we're going to start with capacitors. Before we learn about capacitors, one thing we need to understand about conductors is that when we place a conductor inside an electric field, the charges inside the conductor, namely electrons, because those are the only entities that are free to move, the charge inside the conductor is going to rearrange depending upon the direction of the electric field. So these capacitors are essentially electrical conductors. And what happens is, so let's say I start with a basic form of capacitor. So this is called a parallel plate capacitor. So in this case, we have two parallel plates and they are spaced with some distance, and inside between them is an insulator such as an air, or you could have any another material as well. When there is electric field applied around this capacitor, the electrons are going to move. So I just applied a potential difference. The electrons are going to move from here and then they're going to build up here on this side of the plate. As a result, the other side of the plate is going to have positive charge induced on it. And then the other plate that is facing this positive side now is going to have a negative charge induced on it. The opposite is going to happen on the other side of the plate. So here, as we see inside this, so you have a negative charge induced and you have a positive charge. From our last lecture, by convention, positive, if we have more positive, that is high potential, and then if we have negative, more negative, then we have low potential. And whenever there is a potential difference, it's going to start the flow of current. So as the charge is induced inside this insulator, we are starting to create potential difference, and that potential difference is proportional to the charge that is produced. And if we were to remove this proportionality with the equal sign, we will have a constant here, C, which is called capacitance. And this capacitance is the capacity of a conductor to store charge. So just like similar to resistors, we had this definition where resistance is equal to rho L over A, and rho is the resistivity, which is the material's property, and then L is the length of the wire, and then A is the cross-sectional area. Similarly, capacitance is also dependent upon the material that makes up a capacitor. So specifically, this is equal to A epsilon over D. So A is the area. So if this is a plate, then the area of the plate. And epsilon is the property of the insulating material that is separating these two parallel plates. And D is the distance between these two parallel plates. That is what defines C. It's a constant. Now, we want to understand what happens when there is a potential difference. The current starts to flow. If you want to understand how does the current flow into this equation, we know that current is equal to Q over T, that is the rate of flow of charge. We can also rewrite this as dQ over dt. So small amount of charge flowing through small amount of time. Now this Q from here is equal to C times V, so we can say I is equal to D over dt, C times V. And C is a constant, so we can pull that out. I is equal to C dV dt. this is the relation between the voltage and the current flowing through the capacitor. Remember, for the resistor, the voltage and current were directly proportional to each other, so we got a straight line if we were to draw it on a graph with the V on the x-axis and I on the y-axis. In this case, for a capacitor, we have I is directly proportional to the rate of change of voltage, not just the voltage. Now that we have the fundamentals down, we can move to more interesting things. We need to remember these three things from what we just learned. We need to know the relationship between the current and the voltage, which is I equals C dV dt. And then the relationship between capacitance, voltage, and the charge, C equals Q over V. And then finally, the capacitance itself is defined as A times epsilon over D. A is the area, D is the distance between, for example, parallel plate capacitor between two plates, and then epsilon is the dielectric constant. So now if the two capacitors are connected in parallel and series, how do we know what's the total capacitance? We'll take an example of the series connection first. So these are our two parallel plate capacitors which are connected in series, and we have a voltage difference applied V. These two are generic capacitors, so let's call it C1. It has a capacitance C1 and C2. So here the electrons are going to start to flow from the negative and they're going to move, come here, they're going to build up here, so we have a negative charge build up, and then as a result on the other side of the plate we have a positive charge induced. And similarly, we have a negative charge induced on this side, positive on this side, negative on this side, positive on this side, and negative here, positive here. It might be hard to see the signs here. Just remember, where you have the negative side of the battery, you will have a negative charge built up on that side of the capacitor plate, and then they alternate. These charges that are built up in these capacitors are the same. So Q1 is equal to Q2. We're going to just call them Q and Q. And the reason we just saw that the charges that are induced here on this side of the plate and this one is influenced by the charge on this negative side that is caused due to the flow of electrons from the battery towards the capacitor. From this relation that says C equals Q over V, if capacitance is different and Q is the same, then V has to be different. So the voltage drop for capacitor 1 is V1 and this is V2. Now from KVL we know total V is equal to V1 plus V2, and we can write V in terms of C and V. So we can write V as Q over C. Q over C is equal to Q1 over Q over C1 plus Q over C2. And we can factor out Q and cancel, and we're left with 1 over C is equal to 1 over C1 plus 1 over C2. And then we can take the inverse of this to get the final capacitance. As you can see, this is the opposite of how resistors behave. When we have resistors connected in series, the total resistance is simply equal to R1 plus R2. So this looks very similar to how the resistors would behave when they're connected in parallel, actually. So now let's move on to the other possibility when the capacitors are connected in parallel. So we have capacitors connected in parallel, and then we have a voltage difference applied V. So again, this is C1, C2, and negative, negative, negative. On that side, positive, negative, 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 positive, positive, positive. In this case, when the capacitors are connected in parallel, the voltage drop across them is the same, similar to how we have it in the resistors. So V1 and V2 is same as V. V1 is equal to V2 is equal to V. Again, from this relation, C equals Q over V, if V is the same and C is different, Q has to be different. So in this case, Q is different, the Q1, and this is Q2. We know that charge is always conserved, so total Q is equal to Q1 plus Q2. And we can write Q in terms of C and V as C times V. So we get CV is equal to C1 V plus C2V, and we can factor out V and it gets cancelled, and we're left with C equals C1 plus C2, and that's the result. So if you just want to remember, just remember that for the resistors, what we learned, and then for the capacitors, it's just the opposite of that. The next thing that we want to learn about capacitors is the energy stored in the capacitors. As we just saw, when we have a capacitor, it's in the electric field, placed in the electric field, there's a charge built up in it. And then the charge that is built up in this is stored in the form of energy, specifically electrostatic energy. And then the energy that is stored inside the capacitor is given by, let's call it E, half CV squared, where C is the capacitance of a capacitor and V is the potential that is induced, potential difference that is induced inside the capacitor as a result of the electric field that is applied around it. Let's derive this. We know from the previous lecture, power is equal to V times I. And what do we know about the current for a capacitor? Is equal to I equals C dV dt. So if I replace V and I with C dV dt. And what do we know about power and energy? Power is the energy per unit time, that is E over T. We can also rewrite this as differential, so we can say d dt E is equal to V C dV dt. If I take the integral on both sides with respect to time, so d E dt, integral over time, same thing on this side, CV dV dt, and the integral over time. What we will see is, from this, after we solve the integral, we're going to get E, which is the energy, C V squared over 2. How did we get that? This is by solving this integral. So that's the energy stored inside the capacitor. And let's just put that down here. So the energy stored in the capacitor is equal to half C V squared. This is all I want to teach about capacitors in this lecture. Next we'll move on to the inductors. So I do have one question for you before we move on. The question is, I have 3 capacitors C1, C2, C3 that are connected in such a fashion, and I want to calculate the total capacitance between point P and Q. So I'll leave that as a question for you. You can put your answers in the comments below. Now we can move on to inductors. Simply put, inductor is a coil. It's a wire, and that symbol is this. And then when we apply a potential difference, it will cause the flow of current. And then what's happening is this coil has a property called inductance. Inductance is a property of electrical material to oppose the flow of current. Let's say this is V, that's the potential difference applied, and there is a current flowing here. So I is causing a potential induced. We call it back EMF. So that's the potential that is opposing the flow of current. So let's call it V H just to differentiate it from the potential difference that is being applied. So here this VH that is induced inside the inductor is proportional to the current that is flowing through the inductor. And we were to replace this proportionally with equal, we'll see that we'll replace it with L, which is the inductance for that inductor, times I. I'm going to drop this H just so to keep things simple, so we'll just call it V. But remember that I'm not talking about the V that is applied, I'm actually talking about the V that is induced inside the inductor. More precisely, this V is not simply equal to Li. This is produced because the current is flowing, so it's proportional to the rate of change of current. So V is actually equal to L di dt. That's a very important relationship. Let's just put it here. V equals L di dt. Similar to a capacitor, inductors also store energy, and the energy that they store is given by half Li square. And similar to capacitors and resistors, the inductors can also be connected in series and parallel. I'm going to spare the details for you. So we just need to remember when the inductors are connected in series, let's say L1, L2, then the total inductance is L1 plus L2, similar to resistors. If they're connected in parallel, then it's 1 over L equals 1 over L1 plus 1 over L2. That's all I'm going to cover about inductors without going into further details. Before we wrap up this lecture, let's put it all together for all three passive electrical components so that we have it all in one place. The summary chart behind me is what you want to take a snapshot of, and you can use it as a cheat sheet as you wish. So I'm going to get out of the frame for a little bit so that you can take a snapshot. I'll be back in just a second. Alright, we have already covered a lot of these things. I'm not going to go into the details again, but I'm going to point out some of the important things that we should remember for every component. For example, for an inductor, we need to know that the voltage is equal to L di dt. For resistor, we need to know the Ohm's law, V equals IR. And for a capacitor, we need to know the current is equal to C dV dt. Similarly, we have covered the power and then energy stored inside the inductor given by half Li square. And for a capacitor is equal to half CV square. So inductor and capacitor, they both store energy, whereas resistor, it dissipates in the form of heat. Now there are units: Henry for inductor, ohms, and farad for capacitor. One thing we haven't covered is really important to know that when we have a DC current flowing, in that case, inductors they act as our short circuit. And the capacitors, on the other hand, act as an open circuit. This is only true when we have DC current. When we have AC current, things are changing. So what's happening inside the inductor? The current that is flowing is changing, and it's changing slowly. Similarly, for a capacitor, the voltage is changing. Remember, we have charge that is being induced, and that charge causes change in voltage, and it's happening over time. Finally, the series and parallel connection. We have already learned that, so I'm not going to repeat again. So this is all I want to cover in this lecture. Just to recap, in the last lecture and this one, we have learned the basic electronics theory. We know what is power, current, and voltage. Now we know what are the three passive electrical components: inductor, capacitor, and resistors. There are other important things that we need to know, which we will cover throughout the rest of the course, such as RC circuit, where you have resistor and capacitor connected together in a circuit, and then that can be used as a filter. We'll learn about it, so don't worry. What I would suggest before closing is that you do as many problems as possible for circuit analysis so that you really know how to solve when you have different electrical components connected in the circuit. That's all for this lecture. Thank you for joining me again, and I will see you in the next one. Thank you. Bye.